Greetings. Welcome to week 8 of our distance learning. I think this will be our last week for this school year's lesson. So, for those who are going to be watching this and who've watched the previous 7 videos, congratulations, and I hope that you actually do the work well for this one. And I do hope that you stay well. Anyways, for this week, we're going to be talking about general logarithmic equations. Not all equations in logarithmic form can be solved in exponential form, right? In which case, we'll have to use logarithms and technology in order to solve it. So before we actually go over our lesson for the week, let's visit the online safety guidelines as what we usually do. And here we go. All right, so please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. In addition, this session may not be recorded without the instructor's consent. The description of the applicable procedures is provided online in the Student Rights and Responsibilities Handbook. Thank you for your cooperation. So as usual, this particular phrase, what this means is that this pre-recorded video could not be shared without my consent. So if you feel that sharing it with a friend of yours would help them, definitely do let me know so I can actually issue or write a written permission allowing you to actually use the video. Anyways, if you'd like to read more of the online responsibility and safety, you can definitely go to the go visit the PG portal and look for the student handbook over there. Or if you don't want to navigate the PG portal, you can always go to our Google Classroom, scroll all the way down to one of the earliest entries, because I definitely put up a link there to the student handbook. Okay, now that this is out of the way, we can actually begin with our lesson for the week. Okay, so as I mentioned, our lesson for the week is about general logarithmic equations. Okay, so in this particular case, because usually if the logarithms would not be an exact number, which is rational, so it's either a whole number, integer, or maybe a fraction. Okay, if that were the case, then an exponential form would be sufficient to solve that. However, if it's not possible to actually determine an exact exponent, then we'll have to use technology in order to determine the logarithm. All right, so the objectives for the week. So at the end of the lesson, students are expected to, one, utilize technology. So either we use a graphing or scientific calculator to solve logarithmic equations. And last objective for the week, to apply logarithmic equations by solving word problems. All right, so let's go over that. Okay, so here now is our review and preview. Okay, so last week, we studied properties of logarithms and how they are used in order to simplify certain logarithmic expressions to become a singular logarithmic expression. After that, we convert the logarithmic expression into an exponential one, and then we solve the exponential equation. But as I mentioned earlier, sometimes it is not possible to solve them, as the answer might be irrational. So, for those that don't remember, an irrational number is a type of number which has non-repeating decimals and non-terminating decimals. So examples of irrational numbers are pi, square root of 2, and so on and so forth. right? So take note that irrational numbers are still real numbers, right? They are not to be confused with imaginary or um, undefined numbers. All right, so here we go. So here is the first example for solving a logarithmic expression. So logarithm of 7 plus 2 is equal to x, right? So if you would like to try this out on your own, of course, you are free to do so. You may pause the video, try it out on your own, and then when you're ready, you can definitely unpause the video and we can go over your answers. All right? I think that's enough time for you guys to have paused the video and unpaused it. So let's try to go over the solution and see whether you got the correct answer or not. All right. So in this particular part of the solution, we're going to be, of course, talking about this, but later I will definitely solve it on the whiteboard. But in order to show why it requires technology in order to solve it, we are going to see whether there is no possible exponent we can actually think of. So from logarithm of 7 plus 2 is equal to x, we can actually convert that into exponential form by following the procedure below. So first, we move the plus 2 by subtracting 2 to both sides. Then after that, it becomes logarithm of 7 equals x minus 2. We convert to exponential form. Take note, this logarithm has no base. Thus, its base is understood to be 10. Thus, from this logarithmic expression, it becomes an exponential expression. Now, this is the problem, right? So, 10 raised to the x minus 2 is equal to 7. The problem is, 7, it cannot be expressed as an exact power of 10. 10 raised to a particular number, right, could not be 7. So in which case, we cannot actually solve this through any of our regular methods. Thus, we will definitely rely on using technology to solve this one. Okay, so the software I'm going to be using here would be Desmos, but later I'll of course show you how to do it with regular scientific calculators or even your phones. So let's go to Desmos because that is all right. So here we go. So here we are at Desmos. I'm gonna start graphing. All right. So here we are. So there are actually two ways of doing this problem, right? So first, I'm going to show it through the graphical approach, and the second approach is to solve it using a bit of algebra, right? So take note of the main equation. We have logarithm of 7 plus 2 is equal to x. So what we're going to do is we're going to let the left side be equal to y, and then the right side also equal to y. We're going to graph and then see where the intersection is. That way, we can definitely determine what the correct answer is. So let's go back to Desmos. Okay, so first up, y would be equal to, so if you're using Desmos in your laptops, you can just type logarithm. That should be it. So it's logarithm of 7 plus 2. All right. So that would be the graph of y is equal to logarithm 7 plus 2. Next. we're going to type the right side. So y is equal to, the right side of the equation is simply x. There we go. Right? So therefore, the answer is, okay, so for what value of x would the two graphs intersect? It intersects at x is equal to 2.845 or 2.85 if you would like to just keep it to two decimal places. Right. So how do we actually solve this? Using regular calculators, scientific calculators, of course. So we'll go back to our whiteboard. Oh, wait, we're having a bit of difficulties here. And here we go. Okay, so for this particular problem, all we have to do is to actually use a calculator to evaluate this expression. Okay, logarithm of 7 plus 2. So the calculator I'm going to use for now is Desmos. Desmos. Right, so I'm going to clear this. Okay, so if you're using the phone or tablet app for Desmos, or you're using a tablet and or your phone, and then you just access Desmos from there, you can always find logarithms by accessing the keypad, going through functions, and then looking at miscellaneous. So this is where you will find logarithms. Okay, so if you need if you need logarithm to the base 10, it's simply this one. If you need it in a specific base, it's actually this, right? So since our expression is simply logarithm to the base 10, so we're using this one. So the problem is logarithm of 7. We're going to close that and then plus 2. All right. And then, of course, we simply get the answer 2.845 or 2.85. So since that expression is already equal to x, then our answer is just simply 2.85. Oops. All right. Okay, so this one is very easy example just to illustrate how we're going to do it. So as we go further, you'll notice that the examples become slightly more difficult. All right, so let's go back to our lesson. Okay. Okay, so here we go. So even if we check that, so in its exponential form, so since x is about 2.85, so 10 raised to the x minus 2, which is 2.85 minus 2. 2.85 minus 2 is 0.85, and 10 raised to the 0.85 is simply 7.08, which is approximately 7. Now take note that the answer we got was slightly higher than 7 because we had to round our numbers up. As I mentioned, usually if the exponent is not exact, then it is irrational, meaning it's non-repeating and it's non-terminating. So therefore, in order to actually reach the part where it has to terminate, you will have to, of course, round your answers. Okay, so this one. This is the base change property. Now, this is also part of the properties of logarithm, but I left it out because the base change property is most useful for calculations, not pretty much for simplifying logarithms, but more of for calculating specific logarithms, right? So the base change property is expressed as logarithm of y to the base m. So this is like your regular logarithm. So this one can be expressed as logarithm of y. So take note, in the numerator, it's still the logarithm, the same power, but the base was changed, right? Now, there would be also a denominator. It's logarithm. This time, you're taking the logarithm of the original base, and then the new base is equal to the same base you had for your numerator. Now, what is the purpose? What is the use of the base change property? Now, the base change property is useful because ordinary scientific calculators do not have the ability to actually have the base change into a convenient base. Sometimes you're stuck with two particular bases, which is for 10 and e, right? So thus, a convenient way of being able to calculate a particular logarithm at a base which is different from 10 and e is actually to use the base change property. So logarithm of y to the base m could be expressed as logarithm of y divided by logarithm of m. Now take note, in this particular notation, logarithm y over logarithm m, the base is understood to be 10. Or if you prefer to use e, Euler's number, you can of course convert logarithm y to the base m to the form natural logarithm of y, ln of y, divided by ln of m. So any of these two notations should allow you to compute for it effectively. All right. So here we go. All right. So to compute for the total money saved in the bank, time deposit, we follow the formula B is equal to P times 1 plus R over T. So this one is a very, very common formula, right? This is a balance formula, a total money formula for investments or deposits. So in this formula, B is the balance. How much will the money be after a particular amount of time? P is the principal. The principal is the initial amount which was deposited or invested. R is the interest rate, usually in terms of per year equivalent. So you always have to pay attention whether it mentions annual interest rate. And T is the amount of time that the money was invested or saved in years. All right, so now that we have this formula, the question is, how long would it take a deposit of $10,000? Right? So you have an initial deposit of $10,000 at an interest rate of 5% compounded annually. So this 5% is the interest rate, which is annual. So the reason it mentions it's compounded is because in real life, deposits are usually compounded. That means they earn interest every now and then. And whenever it earns interest, its interest also earns interest. Right. So if you save your money, if you deposit it, and you don't touch it, you don't withdraw anything, after a while, it's going to grow larger, right? So it doesn't grow larger at a particular constant rate. I mean, you could say it's constant, but it's constant in terms of a multiplier constant. So it's exponential in nature, not like linear in nature. So the question is, how long would it take for the $10,000 to become $15,000 if the annual interest rate is 5% and it's compounded annually? All right, so if you would like to try this out on your own, you are free to do so, of course, right? Just pause the video if you need more time, and then when you're ready, you can unpause the video and then look at our solution. All right. Okay, I think that's enough time for you to have paused the video and then paused it. So now let's try to see whether you got the correct answer. So the first part is to identify which of these numbers actually go into which letters. So let's start with the 10,000. So the $10,000, right, is the initial deposit. That means this $10,000 is actually your P. Okay, right? Now, the 5% is actually the interest rate. So that should be your R. Now take note, because this is in percent, you have to convert it into decimal before you actually add it to 1. So instead of putting it as plus 5%, you need to put it as plus 0.05, right? Be very careful with how you put in percentages onto expressions. And finally, 15,000, that would be the total money in the account after a while. So this is your total balance. Okay, so let's go to our whiteboard and continue the solution. Okay, so here we go. So, right, so as I mentioned, the account balance is 15,000. The initial balance or the initial deposit is 10,000. Interest rate is 5%. So how do we begin solving for this one? So this one is an exponential equation, right? And usually, we prefer solving for exponential equations. Okay, so let's try to recall how we solve exponential equations. So for exponential equations, the first thing we have to do is to remove a and k, which is the, or if you'd like, you can just simply do PEMDAS. We'll just add this one first. There we go. All right. Okay. So this one definitely an exponential equation. So as I mentioned earlier, exponential equations, the first thing you have to do is to remove the a and k first. Now, the thing is, this one doesn't have a k, so our only problem is the a. So to remove that, all we have to do is simply divide both sides by the value of a. So we have to divide both sides by 10,000. So 15,000 divided by 10,000, this is simply 1.5 is equal to 1.05 raised to the x. All right, okay, so now here's a problem, because 1.05 is such an unusual base. Therefore, looking for a particular exponent wherein 1.05 raised to that particular exponent becomes 1.5. So what we're going to do in order to save time in solving this is we're going to use logarithms. So we're going to convert this into its logarithmic form. So in its logarithmic form, this one becomes logarithm. The base is 1.05 and the power is 1.5. So this one should give us x. All right. So what we're going to do is we're going to solve this in this particular expression first, and then later, right, because I'm going to use Desmos, and if you remember, Desmos indeed has that particular form wherein you can specify the base, and then later we're also going to solve this in terms of the base change formula. So the only options we have for base change is either logarithm to the base 10 or to the base e, which is the natural logarithm. So in this particular case, we're going to use logarithm to the base 10. So the format is logarithm of the power divided by logarithm of the original base. So take note, power is the um, is in the numerator, original base is at the denominator. Okay, so first up, we're going to solve this one as is. So we're going to again visit Desmos, use the calculator there, and see what it comes to. Oops. Share Desmos. Here we go. All right, so let's cancel this one. So what we are looking for is the logarithm. Okay, so first it's asking for the base. The base is 1.05. Okay, and then the power is 1.5. Okay, so in this particular case, the answer is 8.31. Okay, so this was the answer if we actually do it straightforward. But what if you're only using a regular scientific calculator, wherein you don't have any base change? You're stuck with either base 10 or natural logarithm. That's not a problem. All you have to do, right, is actually base change. So logarithm, so first it has to be the original power, which is 1.5, close the parenthesis. Then we divide that with logarithm, oops, right, logarithm of the original base. Notice how the two answers are the same, right? So this is definitely a good uh, way to show how the base change property is useful in calculations. All right. Okay, so you can, to show further, we'll show that it also works for natural logarithm. So natural logarithm, original power, divided by natural logarithm, original base. All right, see, all three leads to 8.31. And that should be the answer for the problem. Let's see, by going back to the lesson, let's see whether, okay, so we did get here 1.5 is equal to 1.05x. All right, okay, so more solutions. Eventually, we have 8.31 is equal to x. Okay, so take note, if you can actually compute directly, then just go straight forward. If not, then of course go um, base change. All right. Okay. So I hope so far everything's clear. Let's go to actually one last example. All right, so here we go. So in this particular example, it's also an investment or a deposit problem. If the investment is compounded continuously, now continuous compound means that at every unit of time, meaning even at every second, the investment actually starts to earn interest. Now, usually investments earn interest usually at the end of like a month or sometimes at the end of a year. But sometimes um, some investments, you know, are actually compounded continuously. I think it allows, it attracts more people. Okay, so it has like particular drawbacks. So if you'd like to research on it, you are of course free to do so. But the short story is, given a particular interest rate, if you compound it more times in a given year, you earn a smaller interest, but you earn interest more often. Let's say you have an interest rate of 12%. but you will compound it monthly. That means the interest earned is for every month. So instead of earning 12% at the end of 1 year, what's going to happen is you're going to earn 1% interest, but this happens every month. So let's say you put your investment on January, by February, you'll already earn 1% of what you've initially deposited. Okay, this is different from like compounded annually, which means it earns interest at the end of the year. So if you put in a particular deposit in January of next year, it earns interest 12% of what you put up in the account. Right. So this is compounded continuously. So you can just imagine that it is actually for every second, which is actually a lot. However, because it's a lot of compounds, it earns interest a lot of times, then you can expect the interest to be actually much lower for every second. Okay, so eventually, if it's compounded continuously, the account balance formula reduces to B, account balance, is equal to principal times E raised to the RT. Okay, so take note, E is Euler's number, the 2.71, and then R and T are actually exponents of Euler's number. So this is actually what the account balance formula is for investments which are compounded continuously. Okay, so I think the problem is very similar in the sense that it has the same principle, right? It has the same like annual interest, but compounded continuously, right? So, all right, different ways of like, there's like a different amount earned, different percentage of interest earned for every second, right? And then it should total to about $15,000. So how long would it take? Okay, so you might wonder, earlier I get 5% at the end of every year. So from 10,000, it takes about 8.31 years to actually get it to 15,000. Now, if it were compounded more often, but with a smaller interest rate, does it take a shorter amount of time or a longer amount of time? Good question, right? Okay, definitely the answer can be figured out if we actually solve the problem. Right. So if you'd like to try this out on your own, of course, you are free to pause the video, right? Work it out on your own. And when you're ready, unpause the video and let's continue with looking over our solution. Right? I think that should be enough time for you guys to have pause the video, make a decent attempt, and then unpause the video. So let's try to like solve this problem. So let's go over our whiteboard. Okay, so here we go. So as mentioned, the 15,000, that is still our account balance. That is our goal. We need to um, raise our $10,000 initial investment to 15,000. The question is, if this was compounded continuously, how long would it take at 5% interest rate? Okay, so again, um, when you're solving exponential equations, because it's exponential in nature, right? We have to get rid of the a first, so we have to get rid of this. So we have to divide both sides by 10,000. That removes this one. So 15,000 divided by 10,000 is 1.5. All right, so here we are. So now it's 1.5 is equal to e uh, to 0.05x. Now, we are lucky because e is actually a special base. Since it's a special base, then it actually has a special logarithm. Okay? Unless this expression in logarithmic form is simply, right, since the base is e, we have to use natural logarithm. So ln of 1.5. Now take note, there's no need to write the base because if you use natural logarithm, the base is understood to be e. That would be equal to the exponent, which is 0.05x. All right. So we can use the calculator, of course, to solve for ln of 1.5. Let's switch to decimals, our trusty calculator here. Okay, so here we go. Let's clear this up. Okay, so what we're solving for is ln of 1.5. Okay, so the answer is 0.405. We'll just go with 0.41. All right, let's go back to our whiteboard so we can continue with okay, so to solve for x, all we have to do is simply divide both sides by 0.05. Okay, so 0.41 divided by 0.05, right? I think this one comes to about 8.20 or 8.2, right? If you don't believe me, we can of course always go back to decimals and of course check from there. Decimals, our trusty calculator. So we have 0.41 divided by 0.05, 8.20 or 8.2. Okay, so therefore, it takes about 8.2 years for the investment from $10,000 to go all the way up to $15,000 if it were compounded continuously at 5% interest rate. Okay, so if you notice, this was actually much sooner than if it were compounded yearly, which actually makes sense. The longer the time you actually allow on an investment, if it's compounded more times, definitely the higher interest it will definitely accrue. All right. So I hope that wait, let's go back to our main lesson and check whether our answer is correct. All right. So indeed, it's 8.2. All right, is equal to x. All right. So I hope that this lesson has been quite clear. Right. So if not, definitely don't forget that we do have a weekly Google Docs. So definitely do post questions there so I can respond to them the particular time I'm supposed to be there. Right. And do remember that this is the last week that we are to post lessons. So for those who actually were able to see all 8 videos, congratulations. I hope you remember all 8 of them, as you will definitely need them as you go to higher level math courses. So again, this is Mr. Tricino. All right, congratulations on finishing math for this school year. stop share this. All right. So guys, keep safe and bye.